Quasi-Mechanistic Analyses of Impact of Vibrational Dynamic Loading on Characteristics of Clayey and Gravelly Geomaterials. Abstract: a desirably realistic modeling and simulation approach for pavement and related geostructures is to effectively replicate the effects of vibrational dynamic loading, VDL, which is the prevalent mode of loading on practically all live load-imposed structures. In this study, an innovative comprehensive testing regime was designed to simulate the vibrational dynamic loading commonly experienced during in-service of highway and airport pavements. Based on experimental test results simulating a variety of testing and loading conditions adopted for varying geomaterials, sophisticated analytical models, introduced in this paper, were developed. The validity, lucidity, and rationality of the proposed TACH-MD VDL analytical models is pragmatically demonstrated through comparison with experimental testing results. Effective application of these models in the design of highway and airport pavements is ascertained based on tabulated results, graphical plots and analytical discussions. It is rationally derived that the proposed TACH-MD VDL analytical models can be effectively applied for natural and hydraulically stabilized clayey and gravelly geomaterials as well as unbound and bound crushed stone aggregates. Keywords: vibrational dynamic loading, VDL, analysis, analytical models, quasi-mechanistic, clayey, gravelly, geomaterial. Introduction. The application of effective quasi-empirical and analytical models that can facilitate for the precise analysis and structural evaluation of the effects of vibrational dynamic loading is indeed one of the most fundamental prerequisites in pavement engineering. In this study, TACH-MD VDL analytical models that can simulate and account for the effects of vibrational dynamic loading commonly experienced during in-service of highway and airport pavements, are introduced as part of Essential Design Tools 1. Furthermore, consideration of the fact that some pavements will certainly not be subjected to high-intensity dynamic loading, it is imperative that a more realistic approach based on a multi-stage loading regime that takes into account a rebound effect due to post-dynamic static loading stress release, has been made accordingly. Consequently, a number of tests under sustained dynamic loading to simulate critical state conditions and consideration of future increase in load intensity were performed for this sake. 1. It is important to note that the airports that can be appropriately characterized with due reference to the sustained dynamic loading model are the likes of Heathrow and JF Kennedy, which have landings and takeoffs every other minute. 1. Based on the foregoing considerations, therefore, several modes of loading including sustained and multi-stage loadings were meticulously designed and carried out on specimens that represent typical pavement and subgrade materials as well as structural layer configurations in due consideration of the intensity and direction of the impacted stresses. 1. The reliability and effectiveness of applying the proposed models is explicitly manifested in this paper, whereby explicable discussions are made in retrospect to the pragmatic pavement structural design of aerodromes in Kenya and Somalia. 2 core TACH-MD models for deriving shear and maximum impact stresses. Rutting is one of the most important load-induced distresses frequently encountered in flexible asphalt pavements. The primary mechanism of rutting is associated with shear deformation rather than densification. Clearly, therefore, shear stress is one of the critical factors affecting pavement's performance, hence the serious need to fully comprehend its characteristics in asphalt pavements. Accordingly, therefore, it is imperative to comprehend the loading and stress induction characteristics. However, most conventional pavement design methodologies assume that tire pavement contact stress is equivalent to tire inflation pressure and is uniformly distributed over a circular contact area, a theory which fairly contradicts the actuality. In this study, analyses of the mode of loading, load impact/intensity and loading characteristics are fastidiously carried out by employing the TACH-MD models presented in equations 1-6. Equation 1 defines the correlations between shear stress, load intensity, and pavement thickness, whilst equation 2 expresses the same for tire pressure. Instead of load intensity, the relation between the maximum shear stress and maximum tire pressure, is delineated in equation 3, while the location of the maximum shear stress, is defined in equation 4. On the other hand, equations 5 and 6 are adopted in computing the maximum impact and contact stresses for simulating aircraft landing impact and vehicular contact stresses, respectively. Examples of the analytical results generated employing equations 2, 5, and 6 are provided graphically in figures 1-3. Figure 1 depicts the shear stress profile within the upper pavement layers, indicating the location and profile of the maximum shear stress. On the other hand, the influence of the magnitude of the tire pressure and the initial impact stress on the stress and strain distributions and the resulting profile at varying depths is demonstrated in figures 2 and 3, respectively. The following derivations can be made from these figures: I, The magnitude and characteristic profiles of the shear stress, vertical stress, and vertical strain are dependent upon the contact tire pressure. 2. The maximum shear stress occurs at approximately 0.5, where represents the upper pavement thickness. The shear and vertical stress distribution profiles are distinctly different. 3. The magnitude of the impact elastic strain decreases with increased contact stress. And 4. On the contrary, the secant elastic strain limit increases with increased design/impact stress, which is in agreement with the concepts of dynamic loading effects on limiting elastic strain and KHSSS, kinematic hardening soil small strain, models, 2, 3, 4, 5, 6, 7. 3. Validation of the quasi-mechanistic TACH-MD VDL analytical models proposed/adopted. TACH-MD VDL models for determining progressive deformation. The importance of developing reliable models for characterizing the progressive deformation of foundation ground, pavements, and other geostructures, cannot be overemphasized. The quasi-mechanistic TACH-MD VDL, vibrational dynamic loading, analytical models proposed/adopted in this study are introduced hereafter. Characterization of progressive vertical, axial, and lateral, horizontal, deformation under sustained vibrational dynamic loading. On the other hand, the graphical depictions of the results tabulated in Table I are plotted in figures 4 and 5 in both arithmetic and semi-log scales, respectively. The tabulated data and graphical figures also make a comparison between measured and modeled results. It can be noted that, in all cases, an appreciable fitting of the characteristic curves is achieved for the varying natural and stabilized black cotton soils from the Lake Victoria region of western Kenya. Characteristics of the modulus of deformation of natural black cotton soil, Afmadao, and Barra-silta clays, Somalia, are graphically depicted in figures 6 and 7 for loadings up to 10 million and 1 million cycles, respectively. All the depicted graphs also include a comparison of measured and predicted results. It can be observed that, in conformity with their magnitude of initial stiffness, the Barra-silta clay has the highest resistance to deformation, whilst the BCS registers the lowest. Measured versus predicted BCS results show quasi-perfect superimposition. Further validation of the TACH-MD VDL models is undertaken throughout this paper by comparing measured and geomathematically modeled results. 4 principal results adopted for VDL analyses. Example of parametric principal design parameters adopted for VDL analyses. Table 2 presents a summary of the principal design parameters adopted for dynamic loading analysis undertaken for Bartier and Iron gravels sampled from Somalia. B. Summary of results adopted for analyses of VDL impact. Summaries of the results adopted for analyses of vibrational dynamic loading impact are tabulated in Tables 3V for natural clayey geomaterials and Tables 6-8 for natural gravelly geomaterials. Table 3. Summary of data adopted for analysis of dynamic loading effects on deformation characteristics of clayey geomaterials. VDL characteristics of clayey geomaterials. Simulation of the Afmadao-silta clay foundation ground is undertaken by comparatively evaluating the dynamic loading characteristics of clayey subgrade geomaterials. This involves the comparative analysis of I. Load impact, maximum impact upon contact, characteristics depicting the effects of lime stabilization on black cotton soil, BC, subjected to vibrational dynamic loading. 2. Dynamic loading impact on the modulus of deformation of non-stabilized clayey geomaterials. 3. Decay characteristics of secant stress as a result of cumulative dynamic loading effects. 4. Deformation characteristics of clayey geomaterials under dynamic loading, and v. Cumulative stress strain characteristics of neat clayey geomaterials subjected to vibrational dynamic loading. A. Analysis of load impact characteristics of natural and hydraulically stabilized clayey geomaterials. A. Summary of the results of the impact of vibrational dynamic loading, VDL, on the characteristics of natural, lime and lime-coned treated black cotton soil, BCS, and natural Afmadao-silta clay is presented in Table 9, whilst the corresponding deformation characteristics are graphically depicted in Figures 8 and 9 for VD loadings within the range of 10 million and 1 million cycles, respectively. The characteristic curves in these graphs show that, I, notwithstanding the geomaterial type, deformation is significantly impacted by the cumulative cycles of the VDL. 2. In conformity with their bearing strengths, CBRs, the Barra-silta clay quantitatively exhibits the lowest deformation, whilst the BCS registers the highest. 4 days soak CBRs, Barra equals 7%, Afmadao equals 2%, BCS equals 1.5%. 2. Lime stabilization enhances deformation resistance of the BCS, and 3. The Afmadao-silta clay subgrade. Requires in situ ground improvement. B. Analysis of secant stress decay resulting from cumulative dynamic load impact on natural clayey geomaterials. Modeled decay characteristics of the secant deviator stress of natural black cotton soil, Afmadao silta clay and Bara silta clay are graphically depicted in Figure 10 for loadings up to 1 million with comparison to measured data. The results in Figure 10 show that I. The mode and rate of secant deviatoric stress decay as a result of cumulative VDL is dependent upon the nature and stiffness of the clayey geomaterial, and 2. A very good agreement exists between the measured and modeled, predicted, results. Figure 11 depicts the superimposed VDL stress-strain curves for varying clays. The graph also includes a comparison of measured and predicted results for BCS. As was deduced from Figure 10, the Bara silta clay has the highest resistance to stress decay, whilst the BCS registers the lowest. Measured versus predicted BCS results show quasi-perfect superimposition. See deformation characteristics of natural clayey geomaterials subjected to VDL. Deformation characteristics under dynamic loading of natural black cotton soil, Afmadao silta clay and Bara silta clay are graphically depicted in Figures 12 and 13 for loadings up to 3.2 million and 100,000 cycles, respectively, with a comparison of measured and predicted results for BCS. The results from these figures clearly indicate that I. Deformation, defined in terms of axial, vertical, strain is significantly influenced by the nature and stiffness of the clayey geomaterials, and 2. The impact of VDL is more intense within the initial phase of loading tending to a residual state with increased cumulative loading, Figure 13. D. Analysis of cumulative stress-strain characteristics of natural clayey geomaterials subjected to VDL. The influence of dynamic loading on cumulative impact stress. 4. Equals 3.2 is depicted in Figure 14 for natural Bara and Afmadao silta clays as well as natural black cotton soil, BCS. It can be observed that the Bara silta clay exhibits the highest impact stress, a state that is attributable to its lower plasticity index and higher stiffness, 4 days soaked resilient moduli in, equals 39. On the other hand, the characteristics of the cumulative impact stress plotted against axial strain under vibrational dynamic loading are depicted in Figure 15. The results in these figures show that I. The Afmadao silta clay subgrade requires ground improvement to enhance its resistance to impact stress and reduce the magnitude of deformation, and 2. Black cotton soil, BCS, exhibits the highest deformation strain due to its lower resistance to impact stress, lower stiffness, deformation resistance. 6. VDL effects on gravelly geomaterials. The effects of vibrational dynamic loading on the characteristics of gravelly geomaterials are analyzed in this section 6. Essentially, this involves the analysis of I. Dynamic loading impact on the modulus of deformation of non-stabilized gravelly geomaterials, 2. Decay characteristics of secant stress as a result of cumulative dynamic loading effects, 3. Deformation characteristics of gravelly geomaterials under dynamic loading, and v. Cumulative stress-strain characteristics of neat gravelly geomaterials subjected to vibrational dynamic loading. A. Analysis of VDL impact on modulus of deformation and axial strain of gravelly geomaterials, comparative simulation of pre- and post-construction characteristics. Simulated pre-construction, PRC, and post-construction, POC, characteristics of the modulus of deformation and cumulative strain subjected to VDL on some typical Somalia gravels are graphically depicted and compared in Figures 16 and 17 for cumulative loadings of up to 10 million cycles. It can be observed and derived from Figures 16 and 17 that I. The rate of decay of the modulus of deformation is more drastic for the post-construction gravels, implying that effects of reconstitution/remolding are visibly apparent and that these geomaterials may have been in varying degrees of weathered states culminating in the increase in fines contents, which implies loss in bearing capacity and stiffness. 2. Resistance to deformation under dynamic loading is dependent on the magnitude of both plasticity index and the bearing strengths. 3. The mode of decay is influenced by both the magnitude of the initial stiffness and number of cumulative loading cycles, whereas the characteristic curves in Figure 17 show that the axial deformation, straining, is almost entirely dependent only on the initial stiffness, and 4. Both stiffness decay and straining are more acute within the initial stage of loading. Refer to Tables 7 and 8 for further data correlation and verification. B. Analysis of cumulative deviator stress decay resulting from cumulative VDL impact on gravelly geomaterials. Decay characteristics of the secant deviator stress of some typical Somalia gravels are graphically depicted in Figure 18 for loadings of up to 10 million cumulative cycles. That drastic deviator stress decay occurs within the zone of initial loading can very well be observed from this figure. See influence of VDL and axial strain level on the cumulative impact stress of gravelly geomaterials. The influence of cumulative VDL on the cumulative impact stress is demonstrated in Figure 19, whilst its strain level dependency is depicted in Figure 20 for loadings of up to 10 million cumulative cycles. In both cases it can be observed that the cumulative impact stress increases with both cumulative loading and straining tending towards a residual state after approximately 1 million loading cycles. However, it can be inferred that, whereas the threshold for the initiation of the residual state tendency is virtually clearly defined at this level, that of cumulative deformation occurs at varying strain levels depending on the magnitude of the initial stiffness, plasticity index as well as compressive and bearing strength, refer to tables 7 and 8. It can further be derived that reconstitution/remolding reduces the levels/thresholds of both cumulative loading and deformation resistance of the cumulative impact stress, compare pre-construction, PRC, and post-construction, POC, characteristic curves in Figures 19 and 20. Implication of results in this Section 6, Stress Strain and Deformation Resistance, Geotechnical Engineering, Characteristics for Design. 1. 7. Analysis of stiffness decay and deformation of typical Somalia gravels under cumulative VDL. A. Decay and deformation characteristics. The impact of vibrational dynamic loading on the decay characteristics of secant modulus of deformation and the strain deformation of Somalia gravels is depicted in Figures 21 and 22, respectively, for VDLs of up to 30 million cumulative cycles. It can be deduced that both the stiffness decay and straining deformation resistance largely depend on the magnitude of the initial stiffness, elastic modulus. The results in these figures further make a comparison of the pre-construction and post-construction characteristics, which show that the pre-construction, PRC, barred here gravel with the highest initial elastic modulus 0 equals 133, exhibits the highest resistance to deformation. Note that the maximum strain for this gravel is, equals 1.8%. B. Analysis of VDL impact on modulus off deformation within the initial phase of loading. The characteristic curves depicting stiffness degradation resulting from progressive cumulative vibrational dynamic loading within the initial phase of loading 1000 equals 100,000 are graphically plotted in Figure 23. The following observations and/or derivations can be made from the modeled results graphically plotted in Figure 23. I. There exists a zone of erratic data, within the region of very small strains, the causes of which may be attributable to bedding errors, system compliance, and low load intensity, limitation of transducer resolution. 2. It can be explicitly confirmed that the mode and magnitude of impact of VDL is predominantly dependent upon the initial stiffness of the geomaterial. 3. Application of the TACH-MD VDL models, which were developed within a mechanistic empirical framework based on experimental testing data, is limited within this zone. And 4. The limiting factor, which is the number of cumulative load cycles, depends on the magnitude of the initial stiffness with geomaterials of higher stiffness registering higher cyclic limits, possibly due to the fact that bedding error correction requires higher load intensity for stiffer specimens. Implication of results in this Section 7. Simulation of pavement gravel characteristics within initial phase of VDL for design and construction. 8. Analysis of cumulative stress-strain characteristics of clays and gravels under progressive VDL. Under this Section 8, cumulative stress-strain characteristics of specimens subjected to dynamic loading are analyzed. The analysis includes evaluation of the effects of reconstitution/remolding, which are outlined under several preceding subsections. This is achieved by comparing pre-construction, PRC, and post-construction, POC, results. A. Cumulative impact stress-strain characteristics of Clayegia materials. Figure 24 shows the impact of vibrational dynamic loading on cumulative impact stress of clays subjected to dynamic loading, equals 3.2. It can be noted that Clayegia materials with lower plasticity indices, PIs, exhibit higher cumulative impact stresses and that the Afmadao-Silta clay subgrade certainly requires ground improvement. The characteristics of the cumulative impact stress versus strain of Clayegia materials are graphically depicted in Figure 25. It can be noted that the Barra-Silta clay with the lowest pi exhibits the highest resistance to deformation. B. Cumulative impact stress-strain characteristics of gravelly geomaterials. The impact of VDL on cumulative impact stress of gravels is graphically demonstrated in Figure 26 for loadings of up to equals 10. It can be noted that gravelly geomaterials with higher strengths and stiffness exhibit higher cumulative impact stresses, refer to results tabulated in Tables 7 and 7 in Section 4. It can further be observed that the influence of cumulative VDL on the impact stress is more pronounced within the loading zone of 100,000 1,000,000, 100,000 to 1 million, cycles, after which practically all modeled curves tend to a residual state with increased loading. On the other hand, the characteristics of the cumulative impact stress versus strain for gravels are depicted in Figure 27. It can be noted that the gravels with lower pies and higher strengths and stiffness, elastic moduli, exhibit the highest resistance to deformation. Refer to summary results in Tables 7 and 7 in Section 4. See Cumulative impact stress strain characteristics of typical Somalia gravels under VDL, effects of reconstitution/remolding. The effects of reconstitution/remolding are analyzed through the comparison of the pre-construction, PRC, and post-construction, POC, results shown in Figures 28 and 29. Figure 28 and the correlation between cumulative impact stress and cumulative progressive strain depicted in Figure 29 clearly show that reconstitution of the gravelly geomaterials reduces strength/stiffness and that the magnitude of this reduction is dependent upon the original strength, stiffness, and plasticity index. Refer to Summary Tables 7 and 7 in Section 4. On the other hand, Figures 30 and 31 show the impact of progressive loading on the magnitude of axial strain, deformation, graphically plotted both in arithmetic and semi-log scale for clarity of comparison of this VDL impact on pre-construction, PRC, and post-construction, POC, characteristics simulating the effects of reconstitution/remolding and to enable proper analysis thereof. It can also be inferred from these figures that I. Reconstitution reduces the deformation resistance of gravelly geomaterials, and 2. The magnitude of resistance is proportional to the magnitude of the initial stiffness. 9. Performance evaluation of VDL effects. Structural performance simulation of subgrade and pavement geomaterials as well as discrete layers and composite pavement subjected to the effects of vibrational dynamic loading is to be carried out in 10 mainly in consideration of extreme changes in environmental conditions and factors in retrospect to the limiting design parameters. Based on the prevailing climatic conditions in Afmadow and Huger, locations of the aerodromes to be designed in Somalia, it was deemed imperative that moisture suction variation be analyzed for both suction and dilatancy characteristics under dynamic loading conditions, the comprehensive testing regime of which is included in the testing matrix, modules defining basic protocols and main testing procedure presented in Section 4.6 of Chapter 4 of 1. One of the main influencing factors with regard to the impact of moisture suction variation is the pi. Plasticity index, refer to 10 for the functional and applicable models as well as validation and comprehensive analytical discussions. An introductory example of influence of pi in correlation with mode of loading, dynamic static, is subsequently provided. A. Influence of moisture suction variation. As can be observed from Figures 32 and 33, plasticity index and mechanical stability, particle size and distribution, have significant influence on both static and dynamic strengths of Clayegia materials as well as gravels. It can also be noted from these figures that, in general, the dynamic strengths are higher than static strengths for geomaterials with strengths lower than 700 kPa, equals 700. It can also be noted that whereas both static and dynamic strengths, UCS, reduce consistently for Clayegia materials, Figure 32, the characteristic curves in Figure 33 are rather sinusoidal. This is attributable to the effect of mechanical stability, particle size finds content, as indicated in Figure 33. This fact is verified in Figure 34, which depicts the characteristic curves corrected for particle size effects. Simulation is therefore carried out, in 10, taking the effects of plasticity index, particle size, mechanical stability, agglomeration, among other factors, into account. B. Overall performance evaluation. The overall structural performance evaluation of discrete layers and composite pavements is undertaken in 10. X. Conclusions. Introduction of sophisticated quasi-mechanistic TACH-MD VDL, vibrational dynamic loading, analytical models, which are useful in carrying out comprehensive analyses of the impact of VDL for purposes of detailed design of highway and aerodrome pavements, has been made in this paper. It has further been demonstrated that the proposed analytical models equipped with a variety of application modules, the validity, lucidity, and rationality of which has been explicitly demonstrated, are uniquely functional and effectively applicable for the designated objectives. The following conclusions are derived from the analytical discussions presented in this paper. 1. Vibrational dynamic loading has distinctly significant impact on the geotechnical engineering properties, characteristics, and geotechnical quantities of clayey subgrade and gravelly geomaterials for pavements. 2. As the dynamic loading increases, the deformation and impact stress resistance of the clayey and gravelly geomaterials reduces exponentially with the most drastic reduction exhibited within the initial, primary, phase of loading. 3. Designs based on comprehensive subgrade geomaterials, in situ ground property and pavement geomaterials analyses of the effects of vibrational dynamic loading in retrospect to the maintenance of high standards of QCA are imperative in ensuring achievement of performance-based value engineering, PBV, pavement structures. 4. Deformation resistance is predominantly dependent upon the magnitudes of the initial/original stiffness, elastic modulus, and the plasticity characteristics. 5. Reconstitution/remolding impacts adversely on the geotechnical engineering properties of gravelly geomaterials by reducing strength and deformation resistance, stiffness, making the geomaterials more susceptible to the impact of dynamic loading and environmental conditions/factors. 6. Deformation resistance is predominantly dependent upon the magnitudes of the initial/original stiffness, elastic modulus, and the plasticity characteristics, particularly under vibrational dynamic loading. 7. It is imperative to carry out further comprehensive analyses of the vibrational dynamic loading characteristics during the design stage in order to generate appropriate design parameters. Acknowledgement. The author wishes to acknowledge, with utmost gratitude, the Japan International Cooperation Agency and Kojima Corporation, JICA, for substantially funding the initial stage of this research, the Materials Testing and Research Division, MTRD, Ministry of Transport, Infrastructure, Housing and Urban Development in Kenya, the University of Nairobi and Norconsult for carrying out the initial phase of testing as well as the research teams of Kensetsu Kaihatsu Engineering Consultants Limited and the Kenya Geotechnical Society, KGS, for their relentless efforts in providing the due assistance that culminated in the successful compilation of this paper.